Hello, thanks for listening to this presentation. My name is Robert Garcia, and my teammates Daniel Davila, Xavier Reyes, Young Wu, and I, under the supervision of our advisor Dr. Javad Saif, focused our efforts on wind turbine maintenance management for our senior project. Let's get started. To better organize the work and summarize the results of this project, we'll start with the DMAIC process, which stands for Define, Measure, Analyze, Improve, and Control. The DMAIC process is a data-driven quality strategy used for improving processes. In our case, we define the objective of our project as improving maintenance through data monitoring. In the measure phase, we'll describe the current situation of the turbines. Next, we'll observe how well the wind farm is performing. Then we'll attempt to improve the process by suggesting a solution. And finally, we'll work to establish controls for this process so that it can be implemented and repeated in the future.
So as a preface to our project, our team was tasked by OZSoft, who's a data management company, to prepare a cost-efficient wind turbine maintenance plan for their client AGL, an energy company located in Australia.
AGL is one of Australia's largest energy companies and has been working with OZSoft for over 10 years. OZSoft helps operate, maintain, and optimize its fleet of over 50 turbines. The team has been tasked to do a maintenance framework for AGL. We have been given over 5 clusters of 10 turbines, over 2 years of data, and 13 sensors to work with.
Here's a list of steps for this project. We start from conduct failure analysis, create a MRP, and perform cost analysis.
Transitioning to the measure phase of this project, the team began to understand the current state of the situation by extracting, interpreting, and leveraging data given to us by AGL through the use of Python. Here we've included just a couple brief examples of how the team was able to use Python for analysis. The transition matrix to the left, which can offer valuable insight into the behavior of turbines and their states, will make another appearance shortly. The correlation matrix to the right is just another example of how we can use data to determine relationships between different attributes. For example, reading the table for wind speed and power to grid, we notice a very light-colored 0.8 indicating a strong, positively correlated relationship.
So in order to prepare a maintenance plan for AGL, we first need to perform a failure analysis for wind turbines. This includes investigating things like common causes behind turbine failures, how often AGL's turbines are operational or down in the short and long term, and looking at the average turbine uptime in the entire system. So let's take a look at why turbines fail. Most turbine failure is caused by the blades, aka the propeller, being damaged, or more commonly, the bearing failures within a gearbox. Now, turbines are infamous for having all kinds of failures within their 20-year lifespan, even though most failures aren't really that catastrophic as much as they are annoying because of the need to stop the turbine operation for investigation. Oftentimes, bad weather can lead to most failures, and even if it's just a really windy day, that can lead to external and internal damage that can limit or just straight up stop energy conversion. We hypothesize that routine maintenance, like carefully examining vibration readings, can help reduce downtime in the long run. A simple way of visualizing just how prone wind turbines are to failure is through a fault tree diagram, like you see here. This flow chart shows that if any component highlighted in these blue circles were to experience some kind of failure, then the subsystems that they're a part of, which you can see here in purple, will fail, and ultimately the whole turbine is going to go down. This means that one small component, like the gearbox bearings failing, can outright halt the turbine operation, making wind turbines a very, very sensitive and delicate system. So if we know that turbines can fail easily, that begs the question, how reliable are turbines? Well, we just showed that turbine components are heavily reliant on one another, and something as simple as a really windy day can ironically cause a wind turbine to go down. So to answer that question, we need to first begin our project analysis by creating a reliability model based on the limited data we've researched, which, by the way, is only limited because most turbines on wind farms have been installed within the last 20 years, which is within their end of life. Here, we've created a reliability diagram that shows how reliable a turbine is to remain operational. Just like we saw in the fault tree diagram previously, we see that if one subsystem in this turbine is not really reliable, like the main shaft or the converter, the other subsystems and the overall turbine won't remain operational as often as AGL would like it to be. Now, we did a model equation to calculate reliability, since the exact reliability values for each subsystem depend on several factors, since the components are usually made by different manufacturers, either during the installation process or the repair and replacement process, and they involve things like different material quality or composition builds. Next, we'll take a deeper dive into the operational states of a turbine involving failure.
Implementing Markov chain analysis, which simply models a stochastic discrete time process, where stochastic means random, and discrete time simply means distinct, separate points in time, allows one to determine, only knowing the current state of the system, the probability of transitioning to any of the other possible states after one transition, which in our case means after 1 day. The basic Markov chain shown here gives an idea of how turbines behave in the short run. Last, as an example, we can read the table from left to right. So if we start in the OK state of a turbine, the probability of remaining OK in the next state is 97%. Similarly, if we start in the OK state, the probability of transitioning to turbine error in the next state after 1 day is 3%. Moving on, here we see the same Markov matrix as before, but in a formula that allows us to predict the next state of a turbine, aka after 1 day, but also the nth state of a turbine, aka after the desired number of days. This analysis allows one to gain perspective into a turbine's state much further into the future than the previous one. Simply plugging in 15 days for n, we can see the new state matrix at the bottom, indicating a 95% chance that the turbine will be OK after 15 days. Last, for the state analysis of a turbine, we can calculate the distribution of steady state probabilities, allowing us to know the eventual state of a turbine in the long run, aka after a large n value, and in our case that means after a large number of days. Of course, this kind of analysis provides one insight into the more long-term nature of a turbine. Next, we can incorporate some of our prior analysis to determine how exactly reliable wind turbines are. From the snapshot of data shown for one cluster of 10 turbines, we'll notice in the reliability column that the values are relatively low, hovering around 75% reliability. Also note that in the uptime percentage column, all those values are relatively high, almost reaching 100%. Combining these two pieces of information, we know that turbines fail relatively quickly with these low reliability values calculated for a period of 7 days or a weekly period. Yet their downtime is very minimal. They're still up and operating nearly 100% of the time. Of course, this indicates that maintenance is being performed very frequently, indicating a high cost, and we can also see that and observe that from our data if you look at the MTTR column. That indicates the mean time to repair, so those values are very low, very quick repair times. Thus, clearly, more frequent maintenance is better, though we need to reduce the cost of maintenance. We can do this by proactively predicting or proactively repairing parts using an MRP system. Here, as we look into turbine availability, we notice that the average uptime is 96%. We also notice that turbine reliability is around 65%, and specifically from this chart, we notice that clusters 2 and 3 are the least reliable of the 5 clusters. This information can act as a sort of Pareto analysis, where we can use that information to target these 2 clusters for improvement. Things that we can investigate are the failure causes, and specifically we can look at vibration as it's likely to contribute to those failures.
To further verify our numbers, the team ran a simulation model with over 50 turbines in parallel. We used failure rate lambda derived from our MTTF and ran the simulation for 1 month and for 12 cycles to improve our accuracy. This resulted in about 28.2 days of uptime out of 30, which resulted in about a 95% uptime, which is almost exactly what we resulted in our Markov chains and steady state estimates. The team expects 1.4 billion kilowatts generated per month for the entire farm.
To give a proactive solution, we create a 3-step maintenance cycle: monitor, correct, and MRP. This cycle will go around and around to reduce cost. Another example of monitoring is inspecting vibration on turbine, because vibration is a significant attribute that causes a turbine to fail.
The team wanted to create an MRP model to help ensure that there is a spare part ready to go to help increase uptimes and decrease downtimes. To start, the team needed to make a bill of materials where we separated the turbine into its main subsystems. Next, the team needed the demand, which in our case was our failures. We plotted the number of failures versus number of weeks and found that a constant forecasting model fit the data most appropriately. We found that about 18.17 failures per week is to be expected, which we round up to 19 failures per week. Inputting the demand to our MRP model, the team had to make a little bit more assumptions. We assumed that the lead time accounted for both the repair time and the shipping time associated to each part, that there was no safety stock or initial inventory, and we only scheduled for 2 months ahead. The team ran into a little bit of an issue with our cost analysis regarding our MRP model. The MRP model assumes that once a turbine fails, the entire system will need to be replaced, which is not entirely true. Without key information regarding probabilities and costs, the team decided to find the expected value of each failure and plot that with their MRP numbers. We found an annual cost of $11.3 million. With more data, the team can make significant improvements to our calculations if we were given more about the reliability and costs associated to each part.
To get a better idea of having some safety stock ready in the event of a downtime, let's do a cost analysis of what our proposed solution could look like in one subsystem, like the gearbox. In many cases, maintenance is more reactive. Repairs don't really occur until a failure happens, and then the turbine will go down. Usually, there isn't any safety stock for smaller components, like the bearings, because inventory is more focused on things like the blades, which are easier to detect any issues. This often leads to a turbine being down for more than a day, so the company can order a new bearing. Our solution, on the other hand, aims to investigate problems ahead of time by closely monitoring the drivetrain vibration through control analysis and doing routine oil testing for the gearbox, and those costs are significantly lower than just outright replacing the entire gearbox. And just in case the bearings need to be replaced, our proactive solution involves the master production schedule, which will allow AGL to have a new set of bearings ready to go the same day, meaning same-day repair. In AGL's case of 50 turbines, we determined that with our solution, we could potentially eliminate most gearbox-related failures versus traditional reactive maintenance, which will continue having bearing issues because the problem isn't being treated, since all they're doing is waiting until a gearbox fails before replacing it. And again, that costs hundreds of thousands of dollars to do just for one turbine. By doing proactive maintenance, we found that AGL can reduce gearbox-related costs by nearly 55%. Now, if we had more info from AGL for the other subsystems to do a deeper analysis, like we did here for the gearbox, we'd be able to continue reducing costs across the board and easily save millions across the 20-year lifespan for their turbines.
First method to control is using a control chart. We selected 18 random days and collected 31 vibration rate on the turbine and create a control chart. We can see that the process is not in control and it shows cycle pattern. From the same data, we plot the average vibrations and it is exponentially distributed. After analyzing the data, about 96% of process is in control, 4% was not in control. Next step of control is process capability. We are targeting no vibration on turbine, so we create a process capability chart based on it. Results are saying that the process is within specification limit even though process is not in control. Based on calculation, there will be about 28 unusual vibration per day. In conclusion, the goal of this project is to prepare the right amount of spare parts at the right time to reduce the cost from turbine failure by linking OSISOft database with MRP maintenance system and planning for maintenance using computerized maintenance management system. Our recommendations for AGL for success is first provide true maintenance and replacement cost, consider triennial maintenance schedule, consider new vibration damping tower if there is replacement, invest in any additional sensors such as vibration and temperature sensors, and control and adjust the turbine according to the weather.
Here are the references the team used during the project. That concludes this presentation. Thank you so much for listening. We hope you enjoyed it. Please reach out if you have any questions, comments, or concerns.